we can start now. So welcome for the people who joined this webinar for solutions to stop degradation of the subsea well interface. So Sean, if you can please first introduce yourself and then you can start.
You bet. Let's start with a safety moment. So our safety moment today is contact dermatitis, which is skin problems due to chemical exposure. And this can occur with fluids that are perceived to be a relatively low hazard. The technician in this photo, he's an ROV technician, worked with the common hydraulic oil, always wore his PPE, it's nitrile gloves, but gloves would rip while he was working. He would get oil inside the gloves, and this was the result. Heavy scale, heavy peeling and blistering and sensitivity to chemicals, and this can take a long time to recover back to normal conditions. Let's see. Oh, okay. All right, so I'm Sean Thomas. Let's see, are we in? Here we go. Okay. So I'm Sean Thomas, president and founder of Universal Subsea. I'm an inventor, engineer, designer, dozens of successful products over my career, many of which are still in production or used today. I was at Chevron for 7 years as a subsea equipment expert, including 2 years as global subject matter expert for subsea wellheads. And before that, I was at Vetco Gray, which is now Baker Hughes, of course, for 10 years, including 5 years as global product manager for subsea wellheads, and had a lot of influence into the MS700 and MS800 wellhead systems that are produced today. So if you've worked with any Baker Hughes wellhead systems, you've probably seen equipment that I've designed. John?
Yeah, I'm John Fitzgerald. I'm looking after the business development for Universal Subsea. Spent a lot of time over in Asia. I worked with FMC for 23 years, KBR Grand Hern for about 10 years. Lots of time over in also in the Middle East, the Emirates, Yemen, what have you. So I'm just happy to be here. Lots of experience running subsea wellheads and installing subsea trees offshore time.
Okay, and our two folks that are out today, Leroy Patan is Director of Fluids and Lubricants. He's got 40 years experience developing and marketing offshore fluids. He's product manager for WW Canning, president of Houghton Offshore, and president of Rapid Energy Services. Randy Reich is our COO. He's got 35 years experience, primarily at FMC Technologies and Camera. Okay, so the problem we're here to talk about today is degradation of the subsea well interface, which would include subsea wellheads, subsea tree mandrels, and subsea tubing heads, typically. Also, broader scope would include things like manifold and jumper connections. So this is an ROV shot of a subsea tree mandrel after about 12 years of service in, kind of medium, well, relatively shallow waters in the Gulf of Mexico, about 1,500 feet. You can see a cap to the left of the mandrel. So there was a cap that was installed, over the life of the tree, and irrespective of that cap, there was heavy degradation of the subsea tree mandrel, what we refer to as the subsea well interface. So the sealing profile has got heavy buildups. The H4 external connector profile also has heavy calcareous deposits, and crown plugs are just kind of a mess of debris piled up on top of them. So we can expect that the crown plugs would be difficult to remove. require a lot of cleaning initially, and then relatively high extraction forces. Similarly, for vertical trees, we generally expect that over the life of the tree, the performance of the swab valves will degrade significantly, especially for pressure testing performance. Okay, so the solution we're here to talk about today is our Defender Subsea Isolation Cap, environmentally friendly Defender Stasis preservation fluids, which each prevent degradation of the critical sealing and locking surfaces of these multi-million-dollar wells. And that also addresses a key issue for BOP reliability that we'll look at. So the types of subsea equipment degradation include corrosion of various types, primarily oxide corrosion, although this is mostly oxide corrosion is more significant, water depths up to about 2,500 feet. And as the dissolved oxygen in the water drops off, the amount of corrosion will decrease, the aggressiveness of the corrosion. We can also see galvanic corrosion from dissimilar metals, marine growth, as we see in this picture here. The cap that was on this tree mandrel apparently floated off the mandrel due to gas releases from the well. And so we've got seaweed growing on the profile. And I think this picture is kind of funny because there's deep water prawns living in the little bowl for the crown plug, as well as all around the tree mandrel. Additionally, calcareous deposits are an issue. This is something that's not well understood. We'll look at that in more detail. This are calcium and magnesium minerals that are electrolytically deposited by the cathodic protection system to any bare metal surfaces. And that will occur in all water depths, deep water and shallow water. Mechanical damage is another hazard. And the fifth one we have listed here is methane hydrates, which can cause blockages in the access bore and potential damage to the tree equipment. Any questions? Okay, so many of you people will be familiar with cathodic protection systems. More than 90% of the CP systems used for offshore equipment are passive systems that use aluminum, zinc, indium alloy anodes. And these prevent corrosion by through a sacrificial corrosion of the anode. So this creates an electrical circuit, and so we'll have currents flowing through the seawater from the anodes to what's known as the cathode, which is that's the materials that are being protected by the anodes. And this is an electrolytic deposition process, it's basically electroplating. So these calcareous deposits that occur on uncoated steel surfaces, they act as a coating to prevent corrosion of the steel, and the calcareous deposits will actually substantially extend the anode life. So this calcareous deposits phenomenon is a necessary phenomenon. It's beneficial on things like pipelines where coating has been removed, but obviously any tightly tolerance interfaces, any seal surfaces, calcareous deposits are highly undesirable there, as we'll look at. And these can occur on any metal surfaces that are uncoated, where you have seawater and you're electrically coupled to the anodes. Now, the currents coming from the anodes, they're omnidirectional. They'll follow very complex paths. So it doesn't have to be a line of sight. It'll follow kind of zigzags even. The currents will also pass through very small gaps. And as long as you have a electrically conductive fluid downstream of the gap or in the gap, you will see currents currents will pass through those gaps, and you can see calcareous deposits downstream of the gap. So to illustrate one example, if you had a seal on a wellhead cap, unless those rubber seals are 100% in contact with the wellhead mandrel, the electrical currents can pass straight through the very smallest gaps. So that's why effective barrier seals on these caps are very important, as we'll see. So we talked about some of this. Calcareous deposits are calcium and magnesium compounds. And they can occur on any uncoated metal surfaces. They can even occur inside cracks and crevices. And the deposits, you guys have any experience with calcareous deposits in the field? They can be pretty tightly bonded and fairly hard in hardness, and generally require pretty aggressive scrubbing to remove. The problem with that is if you're scrubbing to remove calcareous deposits, you're also removing base metal. And that can affect your manufacturing tolerances, which is important, as we'll see. And acid washes are another option to help dissolve the deposits. Those require hours of soak time, and they can attack zinc, aluminum, other soft metals, and elastomers. So you've got to be kind of careful with the those acid washes. So back when I was at Vetco, for years and years, we kind of treated in-canal materials as immune to deterioration in seawater. And, you know, we go from carbon steel to stainless steel to in-canal. We're moving in a trend that gives us much better corrosion resistance, but there's other factors that affect general integrity of those surfaces, as we'll see here. So the chart on the upper right of the slide is the galvanic scale for different metals. So this measures the electrical potential for a given metal compared to a standard reference electrode. And in this case, the kind of most common one is a calomel electrode. So you see aluminum, zinc, indium at the very bottom of that chart, and Inconel at the top. So the second table, I've referenced that to the aluminum, zinc, indium anode. Okay, so that gives us driving voltage of the anode versus the other metals in the electrical couple. And we see carbon steel and alloy steel have a driving voltage of about minus 0.4 to minus 0.5 volts, where Inconel has a driving voltage of over minus 1 volt. So that's very clear there. The driving voltage for Inconel versus the aluminum anodes is more than twice as high as alloy or carbon steels. The consequence of that is that cathodic protection systems will be predisposed to deposit calcareous deposits on the Inconel surfaces first, even before, they'll build up more quickly on Inconel than they will on alloy steel. And for surfaces like, well, it's typically any sealing surface, we see very undesirable deposits on the sealing surfaces. Somebody have a question? Okay. So, the thing that led us into this business is our familiarity with wellhead and tree, what are often called corrosion caps. And these older caps and even more recent ones are rarely, if ever, actually designed or tested to contain internal pressure, to verify fluid injection, to verify that you can retain the preservation fluid without leaks. Some of these caps have no seals at all in the cap. Some of them have no locking system. The ones that do have body seals, typically leak profusely during the fluid injection process. The locking systems tend to be, fairly low-cost locking systems, and they will usually, well, due to the pressure during injection, that generates a pressure force inside the cap, which will cause the cap to lift up against the locking system. And that's, the phenomenon by which most of these caps will end up with leaking seals. And consequence of that is that very little preservation fluid is actually injected down into the wellhead bore. Additionally, caps with a steel body or aluminum body may actually increase corrosion of the subsea equipment mandrel that we're trying to protect. Another additional point we'll look at is the water-based preservation fluids that are typically used provide very limited corrosion protection and will generally dissipate pretty quickly after they're injected into the cap. So result is these legacy corrosion caps and preservation fluids do very little to stop corrosion and degradation of the subsea equipment mandrel. Okay, so a quick overview of subsea equipment preservation fluids. Up until the introduction of the Defender stasis fluids, basically all the competing fluids are water-based. Typically water glycol, sometimes straight water, water without glycol, I should say. And so subsea tree or subsea BOP control fluids are pretty commonly used. There's a couple of different water-based subsea wellhead preservation fluids that are used. And additionally, sometimes monoethylene glycol with oxygen scavenger. People inject that into a cap. So the characteristics of the majority of these fluids are heavier than seawater, and they're water-based. They'll typically tend to sink in a well bore. And these fluids will instantly mix with water if you have, any significant agitation. And the one significant thing is being water-based, generally ineffective to actually displace the seawater from inside a cap or the upper bore of the wellhead or tree. Fluids are also electrically conductive, so they won't act as a barrier to the electrical currents from the CP system. Many of these fluids contain volatile hydrocarbons that provide the corrosion protection. Those hydrocarbons will dissipate pretty quickly, and there are known examples where the hydrocarbon additives attacked elastomers. Okay, so just kind of an overview. These legacy caps and fluids provide minimal benefit. They will, in most cases, will allow corrosion and calcareous deposits without any restraint on that. They just basically act as debris caps. Now, another problem I touched on is a large number of these subsea trees will slowly leak or bubble gas from the tree mandrel. Even happens sometimes on subsea wellheads as well during abandonment phase. So as we see in this picture here, the gas release got underneath that steel protector cap and floated it off the top of the wellhead. And then it flipped over. So you can see the cap sitting there to the right next to the jumper connector hub. And so, the mandrel is sitting there exposed to seawater. Okay, so our background in manufacturing. So I used to be, again, product manager for Betco Gray over the subsea wellhead product line. So I had final technical authority for the corporation for managing the wellhead product line, as well as reliability. And certainly coming from that background, we're familiar with the manufacturing tolerances for the external connector profile. They're very tight. The profile and surface finish for the sealing surfaces is extremely tight. To get a gas tight seal with an all metal ring gasket, that gasket profile has to be almost perfect condition. Any scratches, any tolerance problems, particularly if the ring gasket profile is out of round, even a little bit, that will typically cause significant problems with gas tight sealing. So in some cases, the operators will use a ring gasket with the elastomer inserts, but we caution about use of those because the seal grooves on those ring gaskets can actually increase the scratching of the ring gasket profile. They're okay to use once basically, but you generally don't want to use an emergency gasket repeatedly over the course of the well. You really want to reserve those for emergency use rather than routine use. So the current practices in the industry to address the degradation of the sealing surfaces and the deposits on the H4 profile are scrubbing tools. And now we're focusing on the ring gasket cleaning tools here. And majority of these tools don't have any centralization to the equipment mandrel. So you don't get uniform contact between the scrubbing tool and the BX or AX ring gasket surface. And these tools do remove metal from the surfaces. And so they will remove base metal, the inlay metal, and really significant, you cannot maintain any factory type tolerances with these types of tools. And the more often they're used, the more out of tolerance the ring gasket surface will get. We've heard many field reports of these scrubbing jobs lasting more than 30 minutes, up to 2 hours, up to 8 hours. And there's one field report where they scrubbed on one tree for an entire week. And of course, the damage is cumulative. So for the subsea tree especially, you'll have multiple interventions over the well life. You really want to minimize, how much scrubbing you do on that gasket profile. So, acceptance criteria.
Sean, we got a question from one of the audience about what is the AX-VX. So you may want to explain, when you say AX and VX, we're talking about the sealing surface on the top of the wellhead, the tubing spool, or the tree that's inlaid within canal.
Yeah, so the VX profile is the Baker Hughes profile. That's the primary sealing surface for Baker Hughes profile. And I'm just using generic language here. So referring to a couple of common gasket profiles. The AX is the Cameron profile. So if we look at, in the lower right, we have a, or I shouldn't say Cameron, I should say Subsea. We have a Subsea DWHC wellhead mandrel. And so being Subsea wellhead mandrel, this is going to have a AX profile, where typically, well, in almost all cases on the Baker Hughes equipment, you'll see a VX. And FMC also typically uses the VX profiles, and
Ocker too.
Yeah, and Ocker too. And Drillquip, they have their own profiles. They use a lot of Baker Hughes profiles, but they have some proprietary profiles as well. So one really critical issue is that there's no way to do a dimensional inspection on a, on a tree or a wellhead, after it's on the seafloor, as we all know. And so the only acceptance criteria after these cleaning operations is a shiny surface with no scratches visible to the ROV cameras. And of course, the equipment manufacturers will not certify sealing performance after a handoff to the customer or any field cleaning. And similarly, the ROV operators, they won't guarantee sealing performance either. So left with a situation where there's really nobody accountable to ensure sealing integrity of this critical interface. And, even more significant, we should mention that a seawater test will not verify a gas sealing performance for this type of connection, particularly with the standard ring gaskets. And the gas sealing integrity is much more difficult to achieve than a drip tight liquid sealing. So, this exposes the industry to unnecessary risk, as opposed to the alternative of trying to minimize the degradation of the interfaces over the well life, which is what we're kind of getting into here. So since the Macondo incident, there's been numerous changes to drilling and production operations to reduce risk. However, at the connection at the bottom of the BOP stack, we haven't seen much change with regard to risks there. And it's still the same practices the industry's used for decades. They'll do a seawater test when the riser's connected. They'll do mud tests after that. There's no way to verify gas sealing performance. That creates significant risks to the industry of a gas leak below the BOP connector. Any questions? Okay, so technology to protect the subsea equipment mandrels. We need effective barrier seals for certain, corrosion-proof protector cap body. It's obviously going to be preferred to a metal body that will corrode and deteriorate over time. It's also very beneficial to use a non-electrolytic, i.e. a non-electrically conductive preservation fluid. That acts as a barrier to the cathodic protection system and also provides very long-lasting preservation fluid, as we'll look at. So with this system, we have both the isolation cap and the preservation fluid acting to isolate ring gasket profile, mandrel bore, and the external H4 profile from the CP environment, from the subsea environment and the CP system. And with this solution, this will halt all corrosion, calcareous deposits, and marine growth to the protected interfaces. Okay, so here's an image of our Defender subsea isolation cap. So this is the first ROV installable subsea equipment or subsea wellhead protector cap that actually seals and isolates the well interface from the marine environment and the CP system. We use a plastic body, thick wall, high performance plastic body, because it has very long lasting material with no corrosion or degradation. These caps will last many years, even decades in the subsea environment. Additionally, we have special sealing configuration that isolates both the ring gasket profile and the external H4 profile. We've developed special body seals that allow us to get effective low pressure sealing while providing very low installation force to make ROV installation and removal of the cap feasible. With conventional seals, the squeeze force is just way too high to be able to get the cap installed and removed with the modest amount of force available with the ROV. Additionally, we have a special flow path that ensures that virtually all seawater is removed from both the internal and external zones. We've got a heavy-duty ROV lock screw design suitable for multiple uses, multiple makeup and removals on the subsea environment. So that lock screw is very resistant to damage from an ROV and also provides an integral emergency release feature. So presently, we've got 2 US patents for the cap that cover 3 specific inventions in the first patent, and 5 inventions in the second patent. We have a 3rd patent, which has been allowed, we'll publish in early 2022, and a 4th patent pending. Okay, so locking system here is we use a heavy-duty ROV lock screw. It's designed to be resistant to corrosion, galling, and jamming, and it's also sealed to contain internal fluids. Highly resistant to damage from the ROV. It locks positively into a groove of the H4 profile, so it cannot slip under external loads or internal pressure. It's a tolerance controlled design. You cannot over travel the lock screw. It has positive stops in both directions and a very high torque capacity also. You don't have to count turns to avoid damage because an ROV is just really cannot easily damage one of these lock screw mechanisms. So this design, it's tolerance controlled. So when we engage the lock screw, it actually pulls the cap down slightly and creates a controlled squeeze for the primary seal of the cap, which is the face seal at the top of the wellhead mandrel in that photo. And again, we get very high torque capacity with this design, more than 300 foot-pounds in the makeup direction, more than 150 foot-pounds in the retract direction, very high bending capacity, in addition to this emergency release feature. Any questions? Okay. So this shows our flow path for wellhead application, wellhead defender fluid injection. Part of this flow path is pretty well known in the industry, and part of it, the outer portion, so the internal portion of the flow path has been used for many years by most of the equipment manufacturers. What we've done that sets us apart is, so we have this primary chamber internal to the wellhead mandrel. We have a second, what we call second chamber for the H4 zone. And when the fluid returns exit the hose at the bottom of the cap there, we re-inject into the zones outside the mandrel, and thus we fill that secondary chamber with preservation fluid. Then we exit the secondary chamber, re-inject a 3rd time, and fill the annulus below the secondary seal. And this is one of our patented features, is this particular flow path. And it's kind of tricky to get the preservation fluid in, get all the seawater out, and get a really uniform injection of preservation fluid. So one of our newer inventions is our fluid injection flow path for tree and tubing head applications. Also would work for subsea manifolds. Let me back up. So in this case, with the wellhead application, we have open well bore. We use a lightweight fluid for this application. And the lightweight fluid floats at the top of the wellbore, and it floats within the cap as well and displaces seawater downwards. With the tree defender, our innovation here is we have designed the cap to use a high density fluid on the internal bore of the tree mandrel. So the red arrows there we see for the primary flow path, we're injecting high density preservation fluid. And then once that's done, we shift to the second port of the hot stab receptacle. And we inject lightweight fluid into the external, the secondary chamber and what we call the tertiary annulus. That is the two zones on the outside of the mandrel. And this provides the most effective system to displace seawater from the tree mandrel internally and externally, and create fully protected zones with the preservation fluid. Okay, so our primary focus with the Defender product line has been 27-inch mandrels. Obviously, 27-inch H4 is most common tree and wellhead mandrel globally. We have designs for other mandrels, 27-inch stroke whip, various 30-inch mandrels. We have a design for the Subsea DWHC. We have a design for the Technique 8 FMC EVDT tree, which is this tall cap we see to the right. And this technology can be adapted to basically any mandrel or hub design, as long as we adjust the body size to suit the correct mandrel diameters. Okay, so our stasis preservation fluids, we just were not really satisfied with the commercially available wellhead preservation fluids. They didn't last very long. We talked about that. They don't last very long. They have toxic hydrocarbons in them, and they're not effective for being able to displace seawater as well. So our initial preservation fluid is our Defender Stasis LT. This is the first vegetable oil-based preservation fluid developed for the offshore industry. It's the first oil-based preservation fluid of any type approved for direct release to sea. So this is a low viscosity, lightweight fluid. It floats in seawater, it's buoyant in seawater. And so if you inject it into a cap or any kind of closed chamber, it will, in the seawater environment, will displace the seawater downwards. We also have a lower cost Defender Stasis ST, slightly higher viscosity, and it can be used in this subsea environment and additionally for topsides equipment preservation and running tool preservation. It's also a bio-based product using natural and modified vegetable oils. Our third fluid in the Stasis family is our Defender Stasis HD high density preservation and hydrate prevention fluid. And we'll look at a couple of those here in more detail. So the Stasis LT has a specific gravity of 0.93. Again, as I mentioned, it's the first non-aqueous preservation fluid, classified as a subsea wellhead preservation fluid under US regulatory requirements. It's approved for direct release to sea, subsea oil and gas facilities. And as I mentioned, formulated from natural and modified vegetable oils. It's completely insoluble in seawater and other aqueous fluids. So if you inject it into a cap, it will never mix or blend with any seawater or water-based control fluids or brines, or, it's only soluble in other oils. So the seawater environment it's extremely effective as a corrosion inhibitor and will completely displace any and all seawater from the protected zones. Additionally, it's environmentally non-toxic, biodegradable, non-bioaccumulating, and non-sheen forming. These vegetable fluids they're very interesting. They have a naturally high polarity. So that creates a, what do they call it? A van der Waals effect that causes it to, to be attracted to steel and plastic surfaces. So it provides excellent water displacement properties. It's also rated as a dielectric fluid, non-electrically conductive. So it can even be used in as an electrical barrier fluid, for example. And additionally, being non-conductive, it will prevent any calcareous deposits in the zones protected with the preservation fluid. Let's see, so we talked about some of this. Let's see, insoluble, low viscosity, right? Far superior corrosion protection to any water-based corrosion inhibitors, control fluids, or hydraulic fluids. The corrosion protection performance will meet or exceed most petroleum-based fluids as well. And being oil-based, vegetable oil, it's naturally long-lasting and doesn't degrade or deteriorate. Being vegetable oil-based also, it's very compatible with nearly all metals, as well as very benign to elastomers, plastics, and non-metallic coatings. Also has very low toxicity, so it's very safe for personnel, and it would be unlikely to see the type of chemical dermatitis that we saw at the start of the presentation with these types of fluids. They're just, being bio-based, they're just much more friendly to, humans and aquatic life as well. Okay, so our Defender Stasis HD has a high density fluid with a specific gravity of slightly over 1.14. So we developed this fluid to be able to remove seawater from closed cavities, subsea, such as the access bore or bowl at the top of a subsea top of a subsea tree, tubing head, or manifold. So this high density fluid sinks in seawater and then will sinks to the bottom and pushes the seawater upwards. It's environmentally non-toxic, non-bioaccumulating, and non-sheen forming. It is dielectric in the virgin state, and even with seawater contamination, has very limited electrical conductivity compared to seawater. And while any of the stasis fluids will prevent methane hydrates, we developed this fluid specifically to be able to evacuate seawater from the access bore of the tree so that we can create a completely non-aqueous environment in the access bore, completely oil-filled environment basically, and prevent methane hydrates by dewatering the access bore basically. Okay, so this photo here shows one of our kind of lab tests of we call this a seawater displacement test. So we put seawater in the sample bottle, and then we introduce the Stasis HD added to the top of the seawater. And as we see in this photo, the Stasis HD immediately goes to the bottom of the container and starts to displace the seawater upwards. And as you can see in the photo, we have distinct oil and water phase separation during injection. So similar to this test here, we can inject the fluid into a subsea tree just by holding a hot stab over the top of the access bore. And this fluid will displace and sweep just about anything. Well, actually, it'll displace and sweep virtually any fluid that is soluble in water, including water, seawater, water-based control fluids, ethylene glycols, alcohols, monovalent brines. And this next part is kind of unusual. Again, the Stasis HD is a biodegradable oil, but it will also displace and sweep crude oil and refined lubricating oils. Fluid has excellent chemical compatibility with seawater control fluids, glycols and brines, so you don't see significant precipitants. It's compatible with all commonly used metals, elastomers, and plastics, and non-metallic coatings for subsea equipment. And similar to the Stasis LT, very safe for personnel with high flash point and negligible toxicity. So for the operators, there's a significant value proposition. Looking at different types of, the different opportunities to save money, reduce cleaning costs for subsea wells during construction. For the subsea tree mandrel, we have reduced cleaning costs for every intervention. And for a 12 to 15-year tree life, typically operators will typically see at least 5 interventions over that tree life. And so the savings add up. Reduce risk of leaking BOP ring gasket, reduce risk of leaking crown plugs or swab valves, eliminate hydrate blockages during subsea tree workovers. By maintaining crown plugs in good condition, the operator would be able to use a light intervention vessel instead of using a heavy drilling rig. So looking at those cost saving opportunities, in the majority of cases, that will easily pay for the additional cost of the slightly more expensive protector cap. Furthermore, by maintaining the subsea tree, and specifically the subsea well interface in good condition, we can expect that operators can extend the life of not all, but some subsea trees by at least 2 to 3 years. And that will have millions of dollars in additional revenue for the operator. And, obviously pay for the cap many times over in that case. So looking at environmental safety issues, there's a lot of focus on carbon emissions, and eliminating this cleaning and maintenance of the well interface. We see reduced carbon emissions there. Similarly, eliminating hydrate remediation, reducing discharge of methanol during hydrate remediation activities, and reduce risk of methanol injection equipment on the rig deck. We can, based on feedback from some of our customers, we can expect substantially reduced risk of methane leaks from the crown plugs and access valves and swab valves, and similarly reduce the amount of methane that does leak. Significantly reduce the risk of leaking BOP connector ring gasket, which will maintain well integrity. And this reduces, it's a very low risk, but it reduces the risk of a loss of well integrity below the BOP stack. Any questions? So some of our customers and approvers, among other things, our Stasis HD has been reviewed by Technique FMC and approved for use in the top of their trees. Let's see, and we got a little video. I'll see if I can play this. So you see a hot stab here, just with the portion, the lower portion of the male hot stab inserted into the access bore of a FMC vertical tree. The Stasis HD will be flowing from the ports that are visible between the two O-rings here. And the flow is most easily visible on the left side of the hot stab and the right side of the hot stab. It's kind of hard to see because the fluid's relatively clear, but if you watch closely, you can see the flow coming off of the hot stab and flowing immediately downwards into the tray mandrel. So I'm going to say this is a really remarkable property of this fluid, that you can literally just pour it into the top of tray or tubing head or manifold access bore, be able to displace all of the seawater from that access bore. Doesn't matter what well, this fluid will fill most equipment, regardless of the shape at the bottom. You know, it goes from one annulus to the next annulus. So we'll sweep, in most cases, at least 98, 99% of the seawater from the access bore of the equipment. Can you guys see that at all?
We only have a couple of minutes left, so
Yep.
we wanted to see if there was any questions from any of the participants, or they wanted to comment on the issues we're addressing. Maybe they have some personal experience with these calcareous deposits, or I know in Egypt there's a lot of gas production offshore. Perhaps they've seen some of these hydrate formations. We understand that folks are having issues with these tree bore hydrate blockages in places like deepwater Brazil, Angola. Certainly in the Gulf of Mexico, it's a reoccurring problem. Anybody? Anything?
Any questions, guys? Any thoughts?
Usam, are you there?
Yeah, I'm still here.
Okay.
Waiting for any questions.
Yeah. Well, you're one of the fabulous baker men. So have you run into any of these issues? I know you're working on the control side, but have you had to be out there with the ROV scrubbing away on the top of the tree or the wellhead?
Yeah, I haven't been exposed personally to anything, but I heard a couple of years ago about one damaged wellhead that failed some testing. So I think something like this would have managed to avoid this problem.
Well, we're aware of one instance in the Gulf of Mexico where they ran a pack off, and then they went to test, and they couldn't get a test. You know, they pumped away a few barrels of oil-based mud into the Gulf of Mexico, and come to find out they had a leak at the wellhead, the BOP connection. And of course, you know, if you pump away any fluid, or you have a kick and it's got gas and there's solids in the gas kick, and you don't have a connection there, you can jet that metal away on the wellhead or the BOP side pretty rapidly. It acts like a water jet cutter, you know, especially if you've got a lot of solids entrained in the escaping gas. And then once that occurs, unless you're lucky enough, I mean, obviously the BOP stack is going to be fairly ineffective once that well is flowing. So unless you're lucky enough for it to bridge over, you've got a serious problem on your hands. So what we're trying to do is get the word out through presentations like this to make folks in the industry, on the manufacturing side, on the operator side, on the intervention side, you know, that there's better fluids and there's better caps out there to protect these seal surfaces throughout the life of the well.
Yeah, I have one question about something different. In the presentation, you said that the VX gasket test and the BOP test cannot prove the gas integrity of the VX gasket. So
Correct.
is there any way to prove this before production starting?
For the BOP connection, no, there is not. I'm familiar in some cases, the lower connector on a tree, they've ported, you know, a test port to allow, you know, test port from the tree to the lower connector again. Now, actually doing a gas test with that, I think it's feasible, but certainly more practical to do a liquid test. But that's really only feasible for the tree connector. The BOP connectors have never been built with any sort of additional test port that would allow, you know, gas to be provided, say, by an ROV for testing.
Okay, thanks.
So we rely strictly, I mean, it's, you know, you're relying on a seawater test and a ROV, you know, visual inspection. That's the only criteria we have to, you know, judge the reliability and sealing integrity of that connection. And, you know, that exposes the industry to, you know, really, you know, significant risks that we don't need to take.
If you had a significant gash in the top of the tree or the wellhead, you know, you wouldn't be able to maintain your pressure. The only issue is you have to find out about it fairly quickly, because once you start pumping several barrels of fluid away, you run the risk of further eroding whatever's causing the leak in the first place.
Right.
And I've seen that happen. I mean, in Indonesia, we had an issue where we had something caught underneath the gasket, and we pumped a few barrels away. We realized we had a problem, so we pulled the stack. We were only in a few 100 foot of water. We managed to get a seal on the wellhead once we ran the stack and changed out the gasket, but I could feel with my hand, you could feel an indentation where even just a few barrels of seawater started to wash away on the gasket side. Later on, once you, like in the Gulf of Mexico, I don't know what the rules are like in Egypt and the North Sea, but in the Gulf of Mexico, you know, you initially test with seawater when you run like the high pressure housing and you land the stack. But later on, when you're running the, let's say 13.3/8 or 9.5/8 or what have you, a lot of times you're going to be testing with mud, which is even makes it more difficult to find a leak because it's more viscous or thicker fluid than seawater.
Right.
So that's our story. I mean, we hope the folks that participated, and we appreciate you and Ahmed organizing this presentation. And you know, if anybody has any follow-on, if they, like tomorrow night or in the middle of the night tonight, they wake up and said, oh, I wished I asked Sean, you know, this or that, you can go to our website, you know, universalsubsea.com, and our contact information is there.
Why don't we get them to tell us, John, a little bit about their present offshore assets and plans for additional drilling?
Well, this is a society, right? So you got various operators and what have you.
Correct. Right. Understand that, but you know, maybe they can tell us some in some broad overview the industry there in Egypt?
No, currently we are low on activities in Egypt, so we are waiting. You know, the downturn from COVID last year is we are still facing the consequences. So nothing much is going on now in Egypt,
Okay.
sadly.
But
Do you have any wells out there now in production?
Again, sorry?
So do any of the operators have wells in production right now in Egyptian waters?
Yeah, we have many wells, many subsea wells in production, but no new projects.
Okay.
Yeah, I think BP was one of the last ones to do a major subsea development over there, right?
Yeah, last year they started their latest subsea field. It's called Raven in the Mediterranean.
Yeah. All right. Well, fair enough.
Great.
We appreciate it, and thanks again for the opportunity.
Yeah, we would like to thank you, and if no one has any questions, so we can wrap up and close this session. And thank you very much for being with us today.
All right.
Great. Thanks very much. Have a great day,
Bye,
guys.
then.
Thanks.
Bye.
Thanks.